Okay, so the first thing we're going to do is quickly review Outbound sequences. It won't take a second. This part of the chart, these are the S's, right, everybody? And the shapes that are formed over here are figure eights. These are the P's, correct? D's in the middle, F's on the bottom, right? All right, so let's make an Outbound sequence. Let's write an Outbound sequence for chromium. Right here, okay? And I know you already know how to do this, so I'm going to do it very quickly. Remember, we like for helium to sit right here to make this happen. All right, so boom, 1s2, boom, 2s2, boom, 2p6, boom, 3s2, boom, 3p6, boom, 4s2, brap, 3d4. Everybody agree with that? That's simple. You know how to do this. You'll get that right on the test. Okay. But you know what? That's a whole lot of writing just to end at 3d4, isn't it? So there's a quicker way to do this. And that quicker way to do it is called a noble gas configuration. If you find chromium on the periodic table, okay, go backwards like this and find the last noble gas that you went by. Who is this? Who was here in 3p6? Argon. Argon. So do you know what the noble gas configuration for argon is? Well, if you look up here, it's right here. It's 1s2, 2s2, 3s2, 3p6, right? So instead of writing all of this, 4s2, 3d4, you can just erase that and just write argon, and put it in a square bracket, 4s2, 3d4. Now, isn't that a lot easier? Does that make sense to everyone? I mean, that's a lot easier to do. That saves you a lot of writing. So whatever element we find here, you go backwards to the last noble gas that you went by, and you just write that gas in a bracket. Writing this in a bracket is saying 1s2, 2s2, 2p6, 3s2, 3p6. That's what you just said right there. Is everybody with me? Let's do another one just for the heck of it, because these are super easy. What if I asked you to write me a noble gas configuration for silver? Silver. Here's silver right here. Okay? I will go like this. I will go backwards from silver. I'll go backwards, and I'll find the last noble gas. And that noble gas, if we look up here on the periodic table, the last noble gas that is before silver, here's silver. So I'm going to go backwards. Krypton. Krypton is the last noble gas that we go by. So instead of writing all of the stuff for krypton, boom, krypton, we write krypton, beep, beep, boop, put it in a square bracket, and then we write, this is 5s2, all right? And then now we're in the D's. Remember, the D's are one lower, 4d9. Krypton, 5s2, 4d9. That is silver. What do you think about that? That's easy, isn't it? That's called a noble gas configuration. One other model we're going to do right now. All right? Today is all about simplifying things and saving time. So for saving time, do you remember drawing these models? Yeah, you better, because we literally just did it. Let me draw you a model of sodium. We've been doing sodium today, right? Sodium, bip, bip, bip. 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2, 8, 1. That is sodium. Okay. Now, it's important that you understand that when sodium atoms interact with other atoms of different elements, the only electrons that interact are the valence or the outer electrons. Okay? So this, out of this whole model, the only electron that is important are the ones on the outside, is this 1. The middle is going to be 2 and 8 every time. Look, what if I didn't make a Bohr model of sodium? What if I made it of magnesium? Then all I have to do is this. Put a 2 there, and now we're on magnesium. Does that make sense? Did I change anything on the inside? So, again, with the art of simplification, we're going to learn a new model. This 281, that is a Bohr model of sodium, but there's a simpler model called a Lewis structure. Lewis structure. And to do a Lewis structure, you just write sodium, and you put 1 dot beside of it. Done. Here is a Lewis structure of sodium. That's pretty easy. What does this dot represent? This dot represents the 1 valence electron. Okay? Now, let me re-erase this and put the blank periodic table back up on the board. And I'm sure that you remember that if we were making Bohr models, everything in group 1 has 1 valence electron, right? And everything in group 2 has 2 valence electrons, right? There's beryllium. Everything in group, what we call the tall rows, group 3. You could call this group 3 or group 13, right? Depending on if you're counting these middle 10. But everybody in group 3, they would have 3 valence electrons. There's boron. Everything in group 4 would have 4 valence electrons. Here's carbon. Everything in group 5 would have 5 valence electrons. Here's nitrogen. Everything in group 6 would have 6 valence electrons. Here's oxygen. Everything in group 7 would have 7 valence electrons. And there's fluorine. Everything in group 8 would have 8, except for helium, would have 8. There's neon. Does that make sense to you? So it's really easy now to draw Lewis structures. Anybody that's in group 1 will have 1 dot. Like, look, here's potassium. Here's a Lewis structure of potassium. A K with 1 dot. Anything in group 2, calcium. Anything in group 2 is going to have 2 valence electrons. So it'd have 2 dots. Does that make sense? Now there's an order for spreading the dots out. Let's say we're here at aluminium. You can have 1, 2, 3. Does that make sense? This is how easy this is. So let me ask you, and I would ask the people at home as well. What if we were going to draw a Lewis structure for sulfur? How many dots would you need to put on it? 6, because it's in group 6. 1, 2, 3, 4, 5, 6. Now there's an order to putting these dots on here, and I don't really teach it. The only thing that I want you to understand is when you're making dots on a Lewis structure, is they're not really in a circle. I don't know if you've noticed the dots on a Lewis structure are like 2 per side. And I usually start on the right side first. Does that make sense to you? Like let's do neon. Neons obviously would have 8 dots. So I'd say this, I'd say neon, 1, 2, then you put 2 on this side, 3, 4, then 2 on the top, 5, 6, 7, 8. Okay? And there's a last thing about Lewis structures, if you want to be really lazy, which is perfectly fine, is anytime you have two dots on one side, you can just make that a line. A line stands for two dots. Okay? So Lewis structures are very easy. If the lines bother you, who cares? Here's fluorine. Gabby, how many dots am I going to put on fluorine? 7. I'll leave one open on this side. 1, 2, 3, 4, 5, 6, 7. See how there's one missing there? Does that make sense to everyone? So those are Lewis structures. So now I'm going to give you a simple worksheet on noble gas shortcuts for outbound sequences and Lewis structures. Okay?